Hello, everyone, and welcome back to the Algebraic Graph Theory Seminar. This week we have our very own Sabrina Lato, and she is going to be telling us about a spectral Morebound for bipartite semi-regular graphs.
Thank you for that introduction. So to start off, I'd like to just talk about the regular Morebound. So for that, if you have a k-regular graph with diameter d, then the number of vertices of that graph is at most 1 plus the sum as I goes from 0 to d minus 1 of k times k minus 1 to the I. And you can get this just by fixing a vertex. And then you look at, there's a single vertex, you look at all of its neighbors. There are k of them. You look at all of the vertices of at distance 2. They're going to be at most k times k minus 1 of them. And you continue on until you get at distance d, that there will be at most k times k minus 1 to the d minus I of vertices at distance d. You sum all these together, you get the Morebound. And a general question when you have a bound is what happens when this bound is tight. And in this case, there are two simple examples you can see right away, that if d equals 2, you'll have a k regular graph and k plus 1 vertices. So you'll have a complete graph. If k equals 2, then you have a 2 regular graph on 2d plus 1 vertices. So you'll get an odd cycle. And then the more interesting cases are when k and d are both at least 3. And although this is more interesting, there are very few cases that actually meet this bound. So you have the Peterson graph, you have the Hoffman-Singleton graph, and there's a possible 57 regular graph on 3,250 vertices. But these examples are the only ones that could possibly exist, which is a bit disappointing and leads to some natural questions for generalizations. So for the bipartite, one generalization you can look at is instead of looking at a regular graph, you can look at a semi-regular bipartite graph. So here you have the two bipartitions, and one has vertices of valency k, the other has vertices of valency L. And here you can find upper bound of the number of vertices of valency k through that same method, only here it breaks down depending on what the parity of the diameter is. So the diameter is odd, then you count all of the vertices valency k by fixing a vertex of valency k, looking at all the vertices of valency 3, and there will be at most k times L minus 1 of them, and so on and so forth. And when you sum that up, you get this. You can also, when the diameter is even, you do the same thing, only here, instead of fixing a vertex of valency k, you fix a vertex of valency L. So then there are L vertices that are at distance 1 from that. At most, L times k minus 1 that are at distance 3. And so on. And when you sum all of that up, you get this. So there's more that can be said about this bipartite bound, but the point of the talk is about the spectral bipartite Morebound. So we'll leave it at this for now. Just, you have now seen these equations and you'll see them again before the talk is over. So let that be a fair warning. So then, as I mentioned, I do want to talk about what this spectral Morebound is. And what do I mean by a spectral Morebound? Well, for the regular Morebound, you get these two parameters. You get the valency and this diameter. And you end up with this bound. and particularly because it is possible to bound the total number of vertices of graphs given these two parameters. And you also get that when the bound is tight, you get a particular kind of distance regular graph. And therefore, studying this becomes studying a problem in that has other interesting applications to algebraic graph theory, which is part of the whole purpose. So by spectral Moore bound, I mean something that has these parameters being spectral, but still, when the bound is tight, you get an interesting class of distant regular graphs. And the intuition behind why we can do this is that if k is an integer that's at least 3, and you have some theta that's strictly less than 2 times the square root of k minus 1, there are only finitely many k regular graphs that have second eigenvalue at most theta. So in particular, if there are only finitely many, then you know that there must be some maximum number of vertices that a graph with valency k and second eigenvalue theta at most theta can obtain. And will let b of k comma theta denote this maximum number. And then we're looking for some kind of Moore type bound on that. And here the spectral information then is essentially the first and second largest eigenvalues. And before I can state that bound, I need to introduce one more piece of notation, which is this matrix T of k comma T comma C, which is a T by T matrix with constant row sum k, lower diagonal 1 up through C, and then upper diagonal k and k minus 1. And it's not obvious from looking at this, but it is true that for every choice of k and every theta that's strictly less than 2 times the square root of k minus 1, there exists an integer t and some value of c with c at least 1, such that this matrix has second largest eigenvalue theta. So in particular, when we're looking at bounding the number of vertices in a graph with second largest eigenvalue theta, we can use this matrix instead and consider properties of that. And c does not need to be an integer for, in fact, depending on the value of theta, c will often not be an integer, but as long as it's positive or at least 1, it still exists. So now I can say this spectral Moore bound, which is that if you have k at least 3, an integer, and some theta that's strictly less than 2 times the square root of k minus 1, we can choose t and c such that that matrix from the previous slide has second largest eigenvalue theta. And then we get this upper bound on v of k theta. So the first thing to note is that if c equals 1, we just get the Moore bound. If c is greater than 1, we get a bound that's better than the Moore bound because we have given this additional value of information about theta. And then also this bound is tight if and only if there exists a distance regular graph with quotient matrix T of k comma T comma C. So this does give us an upper bound on the number of vertices, and we do get an interesting kind of distance regular, a particular kind of distance regular graph when equality holds. So I'd like to go through an overview of this proof and the techniques used to do it, because those same techniques adapt to give you it for other cases, including the bipartite spectral case, as I'll get to later in the talk. So the main result that we need to prove the spectral Moore bound is this linear programming bound of Nozaki, which says that if G is a K regular graph with n vertices and these distinct eigenvalues theta 1 through theta d, you let fi be the sequence of orthogonal polynomials associated with the k-regular tree. I will talk more about this later. For right now, the main thing to know is that since it's a sequence of orthogonal polynomials, it forms a basis for the space of polynomials. So in particular, if we have any polynomial, we can write it in terms of this sequence of polynomials with coefficients. And if we have some polynomial f of x with positive or non-negative coefficients, f naught being positive, everything else being non-negative, if f evaluated at k is positive, and if for all of the non-trivial eigenvalues, f evaluated at that eigenvalue is non-negative, then we get this bound in the number of vertices. So a quick note on the proof is that you just take the trace of, trace of f evaluated at that the adjacency matrix A, take the spectral decomposition, and use all of these properties to prove it. So once you know what the properties are, it's a fairly straightforward proof. A second note is that it's called the linear programming bound, because you can set it up as a linear program, even if that's not the form that's currently set up in. And in fact, as a linear program, if you take the dual, you'll end up with the bound on spherical codes of Delsart, Goethals, and Seidel. So how can we use this linear programming bound then to prove the spectral Moore bound? Well, recalling our matrix we introduced, T of k, T, C, we can let lambda 1 through lambda t be the distinct eigenvalues of that matrix. And lambda 1 will be k. Lambda 2 will be that second largest eigenvalue. And then we define f of x to be x minus the second eigenvalue times the product over all of the other eigenvalues of x minus that eigenvalue. So we claim that this satisfies the conditions needed for to apply the linear programming bound. First of all, f of k, well, k is the largest eigenvalue of not just this matrix T, but also the graph G. So obviously when we plug that in, all of these will be positive. For the other non-trivial eigenvalues then, we have that theta r must be at most the second largest eigenvalue, which must be at most of G still. Then that must be at most the second largest eigenvalue of this matrix T by the way that we constructed that. So then we know that when we plug that into this equation, this is going to be non-positive, and the rest of these are going to be non-negative. So f of theta r will be non-positive. Then the other two things concern the coefficients in terms of the sequence of orthogonal polynomials. So before I can talk about that, I need to talk more about those polynomials. So I said that was the sequence of orthogonal polynomials associated with the k-regular tree. So the k-regular tree is exactly what it sounds like. It is an infinite tree where every vertex has the same valency. And by studying this, by just looking at a small example for a little bit, we can quickly convince ourselves that the k-regular tree is distance regular. So what that means is that if you have two vertices, A and B, that are at some distance m, then the number of vertices, C, that are at distance I from A and distance J from B will depend only on this distance M and the values of I and J. So we can denote that to be some constant, PM of IJ, which we'll call the intersection number. And if you just look at the subtree for a little bit, you can convince yourself that this is true for these graphs. And distance regular graphs are well studied. They have a lot of equivalent properties. One of those properties is that if A is the adjacency matrix and AI is the distance adjacency matrix. So in AI, two vertices A and B are, the AB entry is 1 precisely when A and B are at distance I and 0 otherwise. So we multiply A times this distance adjacency matrix AI, then we get it in terms we can write it as a linear combination. This is, I think, not the traditional notation, but so we can write it in terms of the A plus I plus 1, I and I minus 1 adjacency matrices. And for this graph, the K-regular tree in particular, we end up with this sequence of, with these relations. And in particular, this can show us inductively that the distance adjacency matrices are polynomial in terms of just this matrix A. So we can define a sequence of polynomials Fi of X such that Fi of A is the distance adjacency matrix. And when we do that, we end up with this recursive relationship. And in particular, this satisfies a particular kind of three-term recurrence, which by a theorem that's usually attributed to Favard, it means that it's a sequence of orthogonal polynomials. So formally, to define orthogonal polynomials, you need an inner product. This inner product is based on an integral in terms of a measure, but informally, for the purposes of this talk, it satisfies this three-term recurrence. Therefore, it's a sequence of orthogonal polynomials. Therefore, we can apply various properties of the orthogonal polynomials, which I will do and ask you to trust me on that. So we define this sequence of polynomials in terms of the adjacency matrix of the K-regular tree. But if we instead consider a finite K-regular graph, these polynomials still have combinatorial meaning. So in particular, for an adjacency matrix of a finite graph A of G, the matrix Fi of A of G counts the non-backtracking walks of G. A backtracking walk is exactly what it sounds like. It's where you have the sequence where you follow an edge to a vertex and then follow that edge straight back. So if the sequence ABA appears in your walk, it's a backtracking walk. If the sequence doesn't appear there for any choice of vertices, then it's non-backtracking. And then when we go back to the linear programming bound, therefore, I mentioned you prove this by taking the trace of F of A. So when equality holds, And then you expand this out both in terms of that definition and in terms of the spectral decomposition. So when equality holds for the spectral decomposition, you get that f of theta r equals 0. For the regular definition, you're looking at fi trace fi of a must equal 0. In particular, if these fi's are positive, then this trace must equal 0. So the non-backtracking, it's like if the fi's are positive for all I up through some t, then you can't have any closed non-backtracking walks of length less than t. So in particular, you can't have any cycles of length less than length at most t. So in particular, if fi is positive up through some t, then the girth is at least t plus 1. And we will see this later. We'll use this later. It will be helpful. So now I want to go over briefly over some properties of the sequence of polynomials associated with the k-regular tree. And the first property is that if we multiply x minus lambda r for all of the roots of our matrix D of k, t, c, we get this very nice expression in terms of the sequence of polynomials. Put another way, if we take the determinant of xi minus that matrix, we can write it this form. This can be shown just by expanding out the last row and column and using induction. But if you wondered when I introduced the spectral Moore bound why we needed this matrix T of k, t, c, this is the reason why. We don't know anything about most of the eigenvalues of G, but we do know things about these eigenvalues of this matrix. Therefore, we can get a lot of leverage out of that. The next property is that if we take that equation and just divide out, that should be lambda 2, sorry. If we divide out by the largest root of the previous equation, then when we write in terms of the sequence of orthogonal polynomials, we get positive coefficients. This is one of the times that I'm saying this is just a property of orthogonal polynomials and ask you to trust me. It is not in the most obvious way right now, but it is true. The next property is that if we multiply two elements of these polynomials together, then when we write it in terms of still the sequence of orthogonal polynomials, the coefficients will be the intersection numbers. In particular, the coefficients will be non-negative. And in a lot of cases, there's like a slight parity argument, and otherwise they'll be positive. And if you keep track of when they'll be positive, you can describe when they'll be positive, so you can determine whether or not this will be a positive coefficient or whether it'll just be 0. But at any rate, it will not be negative ever. And in particular, if we take P naught of ij, then this is just the number of vertices that are at distance k from some fixed vertex in the k-regular tree. And we've seen this before because it basically, this is what gives us the Moore bound. And if we plug k into the sequence that we defined it in terms of the recursive relation, we can also verify that that's the same thing. So then these are the properties that we need to show the spectral Moore bound. So if we go back, this is our polynomial f of x. Using the first two properties, we can write it in terms of this, and then this divided by the largest root, which has positive coefficients. Then these coefficients are positive, these coefficients are positive. Using the intersection numbers, we get that everything's positive. So we can write this as j goes from 0 to 2t minus 3 of I goes from 0 of fi times fi of x, and these will be positive. These were so this was the last two properties we need to apply the linear programming bound. So now we can apply it. We compute f naught will just be, since these coefficients are all 1, it'll just be this equation evaluated at k. So when we divide f of k by f naught, we get this evaluated at k, which, if we work it out, gives us this result. So that gives us the bound. What happens when the bound is tight? Well, then that means the bound is tight in the linear programming bound. So for all the non-trivial eigenvalues, we have f of theta r is 0, which means every non-trivial eigenvalue of the graph is root of the polynomial. The polynomial has t minus 1 roots. So G has at most t distinct eigenvalues, counting back in that trivial eigenvalue k. And then we also have, since we proved that the fi's were in fact positive, with 0 up through 2t minus 3, the girth of G is at least 2t minus 2. So T has at most t distinct eigenvalues. It has diameter d at most t minus 1, and girth G at least 2t minus 2. So the girth is at least twice the diameter, and there's a result in the theory of distance regular graphs that means that G is distance regular. And in fact, the eigenvalues of G will be the eigenvalues of the that matrix T. So it's a distance regular graph with that precise quotient matrix. So that gives us an overview of the spectral Moore bound. And sort of the main thing I want to emphasize here is that even though it doesn't appear anywhere in this theorem statement, what's really pulling all of the weight here is this sequence of orthogonal polynomials that were chosen. Because we chose the fi of x that had a couple of particular properties that we needed. We chose the t of k, t, c to have a nice expression in terms of this sequence. And then this bound is coming from evaluating fi of k. So a natural question is, well, is this sequence of orthogonal polynomials associated with the k-regular tree the only sequence we can use to get this kind of bound? And if it were, this would be a short and very misleadingly titled talk. So it's not. And I like to talk about bipartite, still regular, spectral Moore bound very briefly. So here we can define b of k comma theta to be the maximum number of vertices in one of the bipartitions of a k-regular bipartite graph with second eigenvalue theta. So this is just extending the notation that we used previously. And here we have two different families of polynomials, which we define in terms of our previous ones associated with the k-regular tree. So this these PIs are when we evaluate that at the even entries and the odd entries. For the odd entries, you'll get this extra square root of x, which is the argument of that. Yeah. And just a quick note before I go on, these are still orthogonal polynomials. You can verify that they still satisfy basically all of the properties that I went over previously. And then if we define this matrix B of k comma t comma c, where here again, still constant invoked sum k, still a t by t matrix, but here the main diagonal will always be 0. And then we have mostly ones along the lower diagonal until we get to the c entry. We can't just have a k minus c here, therefore the k minus c needs to go here and we need one more row. And that will just be that k. And we can do the same sort of to take the determinant on expansion along the last row and call them use induction. We get the largest roots. We get essentially the same expression in terms of these polynomials depending on the parity of t. And we use that, can use that to get a bound. And that was done by Cioabǎ, Koolen, and Nozaki. So this is essentially a very similar looking statement to what we had previously. I don't want to dwell too much on it, just the main note here being that this, when the graph is bipartite, this will in general do a lot better than the regular bound is, as you'd hope it should. So you're really making full use of the fact that the graph is bipartite. So when you have a statement that holds then for bipartite regular graphs, a natural question is, well, can you push this in terms of bipartite semi-regular graphs, which behave in many ways very similarly to bipartite regular graphs? And the answer is yes, but we'll need a slightly different major idea here. So the other polynomials were defined in terms of these biregular trees, or in terms of these regular trees. Now we want biregular trees. So this is again an infinite tree where every vertex is one of two valencies, k or l, and vertices of valency k are adjacent only to vertices of valency l. And here, these are not regular graphs, so they're not going to be distance regular, obviously, but they're not that far off. So if we take these two vertices that are at distance 2, we can see that the number of vertices at distance, let's call this A and this B, the number of vertices at distance 1 from B and 3 from A is 3. But if we take these two vertices, the number of vertices that are at distance 3 from A and 2 from B is 2. So the number of so the set of vertices that are so then therefore this doesn't just depend on the distance between A and B. It depends on the distance between A and B and what by and we can define a similar notion to the notion of the intersection number. But here we just do need to specify which part of the bipartition. And I'm going to use this as the definition of a distance biregular graph, which we'll see again later. So a distance biregular graph is, or graph is distance biregular if the number of vertices at distance I from A and B from J depends only on the distance between A and B and the partition that A lies in. And there's a lot more that can be said about distance by regular graphs, but unfortunately for the sake of time, I don't think I can get into that. But for now, the main point is that it's a rather unnatural weakening of distance regularity. So then we want to do the same thing that we did in terms of writing the adjacency matrices as this linear combination of as polynomials in terms of adjacency matrices. But we can't actually do that for the biregular tree, because if we even just look at A squared, that's going to be the second one minus the block diagonal matrix that has K along the first block and L along the second. And that is not a polynomial in A. So to work with this instead, we're going to consider the distance by adjacency matrices. So since A is bipartite, we can write it in this form, NN transpose. And this N is the bi-adjacency matrix, so it's indexed by the partitions of the graph G. And the distance by adjacency matrices are defined similarly, that the ABth entry is 1 if they're at distance I. And here we can write this out to get this expression. But this is unfortunately not polynomial in N. We have these two different terms here, N and N transpose. So we need two variables to define this properly. But if we define it in terms of these two variables, we do get an expression. And this is obviously not a family of orthogonal polynomials, because it's not even a family of polynomials in a single variable. But if we recall back the way that it was defined for the linear programming polynomials were defined for the bipartite graphs, they didn't actually care about these FIs. They cared about when FI was even and when FI was odd. And we can define these the same way. So f Cioabǎ xy comma y is in fact a polynomial in xy. So we can define it as such. And that satisfies this recurrence, which is a little messier than the one we had for the k-regular trees, but the point being, this is still a three-term recurrence. It is a family of orthogonal polynomials. And similarly, we can define the I case, it's polynomial when it's odd, because it's polynomial in xy multiplied by this factor of x. And again, satisfies the three-term recurrence, so it's a family of orthogonal polynomials. And similar to the regular case, to the k-regular tree case, if we were given a semiregular bipartite graph with y-adjacency matrix n of G, this still counts the number of non-backtracking walks of G. So we can get a linear programming bound. These have similar requirements, though here you're looking at the eigenvalue squared. And that's because the way that you show this is you take FA of f of A squared, which is f of this block diagonal matrix. And in particular, n transpose and n transpose n is a linear algebraic fact that they have all of their non-zero eigenvalues are going to be the same. Therefore, every eigenvalue of n transpose is an eigenvalue of A squared, and every non-zero eigenvalue of A squared is an eigenvalue of n transpose. So we can then use the spectral decomposition. We can use this in terms of the eigenvalues of A. And we get the same sort of bound as before. And then also just a quick note here. I never showed you the linear programming bound for the bipartite regular case, but you said K to be equal to L here. This is it. So now I have. Then we claim that this satisfies essentially all of the properties that we needed to apply the spectral Moore bound. So here, again, we have a new matrix to deal with. Here, I'm only going to show it for the bound splits into two different cases depending on the parity of T. So I'm going to show this for the odd case. The same things can be applied for the even, but it's a little cleaner to just work through one at a time. So here, this is very similar to the matrix we had for the bipartite case. Only instead of having constant vote sum K, it has vote sum alternating between K and L. And again, you have the C term here, which is matched there. And sort of the main reason to work with this matrix is that if you have the distinct positive eigenvalues, sorry, that's square root on the wrong term. So if you take Z minus lambda r squared over all of the eigenvalues, you can write this in essentially the same form that you wrote in terms of the sequence of orthogonal polynomials previously. This is still lambda 2. So this is, again, if you take that divided by the largest root, the same properties of the orthogonal polynomials tells you that these coefficients will be positive. And there should be a +1 here. It's a little trickier to work through this because you do need to pay a bit more attention to making sure the matrix multiplication is defined when you work through multiplying PIs and IIs. But in this case, if you take II times IJ times this Z, then you can write this as a sequence of, you can write this in terms of the polynomial PM. And that will always have positive coefficients. And if you evaluate it at P0, you'll get that same term as you did previously. So this is all the properties that I showed, walked through for the regular case, still applies for this bipartite semi-regular case. So we can go ahead and compute that. So here f of z is this polynomial, which, using the properties, can write in this form. These are positive coefficients. That CZ should be, yeah, okay, yes. These are positive coefficients. These are positive. When we multiply it all out, sorry, we'll get that the coefficients are positive. This F0 term is just this evaluated at KL. So F of KL over F0 is this evaluated at KL, which, if we plug that into the formula, gives us this bound. And as I said previously, you can work through all of those examples with the parity of T being even instead, and you get this bound. So I told you at the beginning of this presentation to kind of not necessarily remember, but recognize when you see again the bipartite Moore bounds, but semi-regular graphs. And here, if c equals 1, that's precisely these. And the parity of t is, the parity might look different, but that's because the parity of t will be one more than, this value of t will be one more than the diameter if you're actually looking at a graph. So these are, so when c equals 1, this gives you exactly the bounds you'd expect to have from the bipartite Moore bound. And again, what happens when the bound is tight? Then it's tight in the linear programming bound. So we have all of the non-trivial eigenvalues squared are roots. There are t roots. All the non-trivial non-zero eigenvalues squared are roots. There are t roots. So there are t minus 1 roots. There are 2t plus 1 distinct eigenvalues, because you have the two trivial ones now. You have plus and minus square root of KL, and you have 0. And you add that to the 2t minus 1, and you get that. So it has 2t plus 1 distinct eigenvalues, so it has diameter at most t. And then this coefficient fi is positive for all I goes from 0 to 2t minus 2. So the girth is at least 4t minus 2. This follows the same way as it did in the regular linear programming bound case. You get this extra multiple of 2 showing up because that's essentially what the polynomials are, but that tells us that G has girth G that's at least 2D minus 2, and G is distance biregular. Again, this can be shown, but also if you're familiar with theory of distance regular graphs and bipartite distance regular graphs, you should probably believe it, because the requirement on, we can know that if G is a bipartite graph with girth G at least 2D minus 2, then it's distance regular. Therefore, if it's a semi-regular graph, it's very believable that this should be true, and it is. So that's everything.
Yes. Are there questions for Sabrina? Suppose I can start with a sort of big, vague one, which is...
I can't hear you right now.
Sorry, can you hear me now?
Yes.
Okay, so I'll start with a sort of large, vague question, which is how much, if any, of this machinery could you get to go through if you wanted to think about 3 valencies in like a 3-partite graph? And would there even be something meaningful to think about there?
I suspect there wouldn't, but...
I kind of suspect that too, but I don't know why.
Well, in a lot of cases, sort of a lot of results from bipartite, from regular graphs can sort of be generalized to bipartite semi-regular, just because the bi-adjacency matrix essentially stores all of the information you need about it. But yeah, even just things like distance biregular. One of the definitions for distance biregular is that it's a non-regular graph that has every distance partition is equitable.
Right.
So you already not. So if that's true, you'll only have 1 or 2 possible valencies. Therefore, I wouldn't suspect anything interesting.
Fair enough. Other questions?
I was wondering if you have any like specific examples of the biregular bound to be tight?
I do, in fact. It sounds like I finally finished, but I actually haven't.
No, yeah.
Yes. So if you have, for example, the partial geometry and 984. So this is seen as an structure. You have points and blocks. Every point is incident to 9 blocks. Every block is incident to 8 points. I'm sort of blanking on the rest of the partial geometry, but definitions. But like every for every non-incident point and block, there are 4 different coincidence points that are coincident to both of those, basically. So this other partial geometries work. This is just one that I have worked through. So the quotient matrix gives you this, which is second eigenvalue, square root of 12. If you look at this, this looks like the form for the bound to be tight, just for the quotient matrix, and it is. We can work it out, get that example, and 135 is indeed the number of points for the partial geometry.